All right. So today we sort of continue on. We've talked a little bit about this, but we're going to talk more specifically about the topic of differentiability, which every time we get to this lesson, I think, wow, that would make a great Scrabble word. You'd have to, have someone do one word, you'd have to tack onto it and tack onto it again. But um, so remember that if the right-hand derivative at c is not equal to the left-hand derivative at c, then the derivative at c doesn't exist. Now, if you're looking at a graph, there's several different ways that this can occur. For example, you can have what's called a corner. If you have like an absolute value, that would be a very strong corner. This is a pretty strong corner. It almost always has one of the pieces as a line, but you can see that the slope of the curve as we come towards C from the left and the slope of this curve as we come from C from the right are clearly not equal to one another. So this function is not differentiable at C. You can also have what's called a cusp, and I have difficulty, honestly, trying to explain to people the difference between a cusp and a tangent, vertical tangent, because they're kind of the same. And, with a cusp, it can really easily look like a corner. No one's going to ask you, and I'm not going to ask you on a test or anything to identify which of these is it. Basically, I just want you to see, you're not going to have a tangent at a point like this, where you have these two curves coming in like this. Also, if you have a vertical tangent line, so my drawing is not perfect, but if you think about taking, and I'm going to try to draw it again, but if you think about drawing like a quarter circle, and then at this point draw a quarter circle going the other way. That's what we're talking about there, is that if we drew in the tangent line, it would go like this. It actually goes through the graph, which is why this is different than like the tangent for a circle. So since that line is vertical, its slope is undefined, and therefore the tangent is undefined. It has a tangent line, but the derivative is undefined because the slope of the tangent is undefined. Okay? So you can have a tangent line without having a derivative at a point if the tangent line is vertical. And then discontinuities. This particular one, I'm showing a jump discontinuity, but we'll look at the other ones real quick in just a second. But the problem here is that as we approach x equals c from the right, all the slopes are 0. As we approach x is c from the left, you might think, well, all of those are 0. But remember, we're connected to this point, right? We're connected to CF of C. And so if I'll cheat and use this, were to draw that tangent line, it would look something like that. And as these points to the left of C get closer and closer to C, the line gets steeper and steeper. Turns out in cases like this that the left-hand derivative doesn't exist at all because it goes to infinity. But even if it did exist and was just some really big number, well, the right-hand derivative is 0. So that's not going to work. In addition, if we were to have something simpler, let's say we had a removable discontinuity. So let's draw this. So instead of having something like that, what if we had, I don't want to be drawing a line on this, sorry. So we had something like this. Wish they didn't quite make such a big hole. The problem we have with this is that the derivative at c requires that f of c be defined. Remember that the derivative would be the limit as h goes to 0 of f of c plus h minus f of c over c plus h minus c, right? If f of c doesn't exist like here, well, we've got a major problem. I can't put does not exist into this limit and expect something to come out of it. Now, what if it's the other kind of a removable discontinuity? What if it's a removable discontinuity so that, there's a point up here or something? Well, now f of c does exist, but let's look at the slopes. If I look at the slope over here, very much a negative slope, and looks like it's getting larger and larger the closer I get to c. And from the right, I get positive slopes. Those slopes are not going to agree with one another. So if there's any kind of a discontinuity, then the derivative isn't going to exist. The other kind, and I won't take the time to draw it, but if you have a vertical tangent line, if you have a vertical asymptote, well, the graph doesn't exist there, so you have the same problem as we did earlier where f of c didn't exist. If f of c doesn't exist, this expression is not going to exist either. So one of the interesting things about differentiability is it implies that the function is continuous. College Board loves to ask questions where they do something with this. They'll tell you that a function is differentiable, and you have to think, okay, that means one of the things that's true about that function is that it's continuous. Why is that important? Well, if a function is continuous, then what is the theorem we know that applies? It's one of the existence theorems.
Fa equals to limit.
No. What we've talked about, we talked about like temperature versus gas prices.
Oh, I know what you're talking about. I don't remember what it's called though.
Okay, so this needs to become one that you have, right there at your fingertips. It's the intermediate value theorem. Okay, because if a function is differentiable, that function is also continuous, and the intermediate value theorem works, right? Which says if you have a continuous function on an interval from a to b, then f takes on every value between f of a and f of b. And it really should get to the place, and I know you're not there yet, and we don't use the intermediate value theorem quite as much as some of the other existence theorems, but it should get to the place where you can just spout that off just like that and go, yeah, I understand how that works. Okay? The other thing that differentiability implies is what's called local linearity. This doesn't get tested very much, but as an idea, it's an important idea. If f has a derivative at x equals a, then the graph of f closely resembles a line. What line does it resemble? It resembles its tangent line when you get very close to a. If you just think about, pick any kind of a smooth function. So let's say that we were like, okay, I'm going to turn this plot off. We were looking at 4 sine of x. And let's do a zoom trig Wow, that turned out better than I thought it would. If we pick any point on this graph, so that's at pi over 2, and so let's say I try to zoom in, and I'm going to zoom in at oh, what the heck is that? I have no idea what it's tracing. Okay, so if we decided to zoom in at some point that's close to that, there's my axis, there's my graph, and I'm going to try and put it close to there, and I'm going to zoom in again. And I'm going to put it so that it's really close to the graph, and I'm going to zoom in again. I've only zoomed in 4 times, which is not a ton, and that very much is starting to look like a line, right? If a function is differentiable at any point, if you zoom in enough, it's going to look like a line. What this allows us to do is, you know how you wrote some equations of tangent lines? Why is that important? Well, certainly from a historical viewpoint, it's important because what it allowed people to do is replace a complicated function with its tangent line as long as you were really close to some particular point. And a line is easier to work with than some horrible function. So they're able to go, okay, as long as I'm really close to this, a tangent line is going to give me a really good approximation for the y value of the function for a given x value close to the one that I did my tangent line. Okay, we'll actually use that idea and extend it at near the end of the class. Not this class period, but like, in March. Well, where we'll extend that idea to where it's like, okay, I can make a good approximation as long as I'm really close. How can I make that approximation better? And it turns out that what you can do, instead of just doing a line, you can actually make a polynomial of whatever degree you want to get really super accurate estimates of the function without having to appeal to a calculator or something like that. All right. Notice on both of these that the converse of these is false. So just because a function resembles its tangent line doesn't mean that it has a derivative there, and that's the example of a vertical tangent. And just because a function is continuous doesn't mean that it has a derivative at a point. I mean, these are continuous, but there's no derivative at those points. All right, intermediate values and derivatives. If a function is differentiable on an interval, then the intermediate value theorem applies to the derivative on that interval. That is, if a and b are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime at a and f prime at b. So the derivative can't jump around. A derivative is going to be continuous. It may not be smooth, but it's going to be continuous. Now, one of the things that we have kind of done is looked at numerical derivatives a little bit. So some of you did this on one of the quizzes where you plugged in some values rather than doing it algebraically, but that was the idea that you wanted. So for small values of h, the difference quotient gives you a really good approximation for the derivative. However, the same value of h will usually provide a better approximation if we use what's called the symmetric difference quotient. That is f of a plus h minus f of a minus h over 2h. So instead of just going to the right, so let's say we just went to the right here, and I'm going to try and draw something that, hits both of those. And using that as our estimate, and that's not a bad estimate, but if I went the same distance to, let's make this a different color so that it's more obvious, to this side, and then drew in, I don't know if it's going to let me draw from here. Nope. Stop it. All right. And draw from there through here. Do you see how this one, the second one that we've drawn, looks like it may be parallel to this tangent, right? And so it's generally a better way to go. So rather than just looking to the right, well, let's look to the right and the left. And you, generally speaking, get a better approximation. So grab your calculators and let's do this. So f prime at 2 and we're going to pick some small value for h. Okie dokie. So we can approximate this by doing, what would you like to use for h? Like 1/100th? That feels like that should work. So we're going to do 2 minus 1/100th to the 4th. Oh, let's do plus, that way everything's positive. Minus 2 minus 1/100th to the 4th. All over, what we're really doing, we don't normally take the time to write this, but this would be 2 plus 0.01 minus 2 minus 0.01. I'm just pointing out that the reason that it's 2h is because we're still doing a slope. So let's shove that into our calculator. I gotta find a setting so this doesn't go to sleep quite so fast. It's not like I'm trying to save battery or anything. All right. So I'm going to have 2.01 raised to the 4th minus 1.99 raised to the 4th over, when I do that subtraction, that's going to be 0.02. It's twice whatever we picked for h. And it says that it's 32.008. Yeah, it's pretty accurate. How do you think I could make it more accurate?
0001.
Yeah, make it a smaller h. If you made it a smaller h, you get better accuracy because you're taking a smaller interval. Now, your calculator actually has this built into it, so you don't have to remember the symmetric difference quotient, nor do you have to go, I wonder which h I should use. So on your calculator, this is the second thing that you're expected to be able to do with a calculator on the AP exam. The first one is be able to get a graph in an appropriate viewing window. Okay? Everyone can graph. The appropriate viewing window is one of the things that sometimes students struggle with. I don't know if you guys have ever done things where you're like, you graph it and you're like, okay, there's nothing on the screen, and you have to spend time finding an appropriate window for it. It's one of the things I actually like about the NumWorks calculator. It picks a good window for you. It doesn't always start with, I'm going to go from -10 to 10 on the x-axis and -10 to 10 on the y-axis. It always picks a window where it's going to show you the graph. Anyway, so on your TI, if you go to Math and scroll down some, number 8 is nderiv. This is the second thing you're expected to be able to do, and textbooks don't do it very much, including ours, and students tend to forget that you can use this if it's a calculator active problem. So here's what you do. You're taking the derivative with respect to the variable x. Now you could make it whatever variable you want, but then you have to type an expression that has that variable in it. Our function was x to the 4th, and we're interested at what happens at 2. This vertical bar right here means evaluated at. And it gives you a better approximation than we got. By the way, what do they use for h when they do this? They use 1/1000th. So if you want better than what they gave you, you can do the symmetric difference quotient and, I don't know, use 1/1,000,000th or something. It seems at least that this is headed towards 32. All right. This allows us to do some investigations with things that we might not normally be able to investigate. So for example, if we let f of x be equal to the natural log of x, use the numerical derivative to graph y equals f prime of x. Can you guess the function for f prime at x? Okay, well, let's see if we can do that. So in y equals, I'm going to get rid of this. And I'm going to graph, and yes, it's really, really slow when it does this, but I want the derivative with respect to x of the natural log of x. And you're like, what am I going to set x equal to? Well, if you set it equal to a particular value, it's going to find the derivative of that, and no matter what x is on your graph, you're going to get that value. You're just going to get a horizontal line. So what we're going to do is we're going to say x equals x, wherever it is as it graphs from from left to right, it's going to choose the value of x where the pixel is. And, I'm going to do zoom standard to start with. Now, first things first, you notice that there is no graph to the left of the y-axis. Why is that? Think about the original function, f of x.
It can't be negative.
What can't be negative? Don't ever say it in this class unless you identify what it is.
X can't be negative.
Yeah. Natural log is not defined for negative values, nor is it defined at 0. So I want you to notice that if I tried to trace this to 0, it doesn't give me any y value. And you're like, do you recognize what this graph kind of looks like?
1 over x.
It kind of looks like 1 over x. Let's go into the table and look what we've got. When x is 1, y is 1. Well, that would be 1 over x. When x is 2, y is 0.5. Well, that would be 1 over x. When x is 3, the derivative is 0.3 repeating. That's 1 over x. And so it turns out that you're exactly right. The function for f prime of x here is indeed equal to 1 over x. So we've showed that graphically. That's not a proof, but if you look at all those values and they're always 1 over x, it's pretty compelling. It always matches. So f prime of x is 1 over x for x greater than 0. Now that I've showed you some uses for nderiv on your calculator for finding a numeric derivative and how helpful it is at times, now it's time for the cautionary tale. Yes, sir.
Is this it's not just everything? Or is it
It's the end behavior.
like
That's a simple basic function. Yeah. Yeah. Nothing elaborate or anything. Okay. Thank you. So now the cautionary note. Sometimes the numerical derivative is completely and totally wrong. There was a great seminar that used to be done that was called Lies My Calculator Told Me. Your calculator has limitations. So consider, for example, y is the absolute value of x at x equals 0. So we go back into this, let's quit out of that. Let's say I tell it, hey, tell me the numeric derivative of the absolute value of x. By the way, if you don't know where to find the absolute value, one of the best things on your calculator is if you do second 0, you get the catalog, which lists everything in alphabetical order, and the first thing there is the absolute value. I'm sure it's other places, I just use it here. So the absolute value of x at x equals 0 and it's going to tell you that the derivative is 0. Lies. Absolutely, totally, completely wrong. Why is it completely wrong? Well, let's look at the absolute value function, which looks something like this. At 0, does this have a derivative? No. Why does it tell you 0 then? Well, it's because of the way it's using the symmetric difference quotient. It went a little bit to this side and a little bit to this side and found the slope of that line, which is 0. Okay? So you have to be careful. You can't just use this indiscriminately. Most of the time, it gives you great answers. Some of the time, it just straight up lies to you. Okay, any questions about differentiability? Okie dokie.